Okay, all right, thank you. Let me not forget to thank the organizer for inviting me here and give this presentation. Originally, I didn't think that this will fit in the topic of this workshop, but after I learned a few talks, I see a relevance that this talk is related to that, and I'll explain that in a minute. But what are we looking here? We have a graph. For now, it's a set of degrees of freedom, we may think, which are connected in some way. And we would like to come up with a reduced dimension object with certain properties. So we like to have a huge object, we'll reduce it to a smaller object, that is dimension reduction, but with certain properties. These properties are in some sense contradictory. The first one, if one is sparse, we like to maintain sparsity for the reduced dimension problem. This is doable up to a certain point. And the other thing is that the reduced dimension problem should approximate the original one in some computable norm. And we should be able to improve that approximation by increasing the coarse degrees of freedom. So as you can see, if you come up with a coarse problem and that one can get denser than the original one, you may face the challenge that that coarse problem may require more memory than the original one. If the coarse basis functions are very dense, and when you compute the matrix, you may need more memory. And in some sense, that defeats the purpose of doing this. So why you have a huge problem and you end up with a much smaller problem in terms of degrees of freedom, but you require more memory. So we try to avoid this and ensure both things, sparsity and approximation. Why do you need such a smaller problem? For many reasons. One reason is if you like to run repeated simulation on the huge problem, like Markov chain Monte Carlo methods, things like that, those are in principle infeasible for very large problem, because for every sample you solve a kind of PDE or whatever you're solving, compute the solution and evaluate some function. And in Markov chain Monte Carlo, many of these solutions you disregard because they don't fit some criteria in the method. So if you have a smaller dimension problem which you can solve faster, you can make this decision with much less effort, and that makes the approach that you're using more feasible. And this is one good argument to look at to produce these reduced dimension problems. And all these three requirements that I said, dimension reduction, less degrees of freedom, sparsity, and approximation, I refer by one word. I call it upscaling, okay, or numerical upscaling. All right, so this work is based on a paper that will appear soon in CISC. These are the collaborators, co-authors. Andrew Barker is in Livermore, and Chuck Lee was in Texas A&M, now is a postdoc in Livermore. So they were heavily involved with this work. All right. So this is the outline. I'll specify the model problem in a minute. Then I'll describe the algorithm, how we actually achieve this coarsening procedure, and what are the properties of this reduced dimension problem. So we prove some results. And then I'll give you a lot of examples and a few conclusions. All right. So let's begin. We have a graph. Graph is just a set of vertices. There is no geometry in general involved. And these vertices are related, are paired with edges. So one vertex can have several edges that connects to the sort of so-called neighboring vertices. Neighboring is not in terms of geometry, because in general we don't have geometry. So and now I relate this to for example, to the previous talk. We have this non-local functional. So that was a double integral. We have gamma x, y, and they have ux minus uy, and then we have vx minus vy, dx, dy. This was the non-local operator that was considered in Marta's talk and in the previous talk. So this is a bilinear form A, U, V. Okay, what I'm looking here is a discrete version of this. It's like summation of a pair of indices, and instead of gamma I have k, which is ij, and then we have ui minus uj, and then we have vi minus vj, which I can write in the following form: summation over the indices, and I can introduce some vector de, and if you form this as a long vector u is with component ui at every position. This is one inner product, and then there is another inner product, v, and this is de is what I wrote in the over there. Maybe it's not seen yet, but it's 1 and negative 1. Everything else is 0. This is position I, and this is position j. So this is exactly the difference, vi minus vj. This is the difference, ui minus uj. And this is exactly this one, and it's discrete version of that one. So in graphs, the notion of local or non-local is kind of blurred because we don't have geometry. But from linear algebra point of view, if you look at the adjacency matrix, if you look at the sparsity pattern of the matrix, some rows can have a lot of non-zeros, some rows can be very sparse. So that's why it can handle both cases, local and non-local. And actually in graphs from social networks, such graphs do appear. There are some vertices that are very important, and they're connected to many other things, and there are some others which are locally connected only. So in general, that's why this is a good model for social networks. But that application is kind of controversial. The question is, how do you model a social network? There are many people working in that area. Some of them do mention graph Laplacian, but it's not widely accepted. That's why I also used a more classical application. It's finite volume method, and it's the 2-point flux approximation is actually self-centered finite difference, and that's exactly graph Laplacian. So, but there we do have a geometry, and the sparsity is regular, okay, depending on the volumes that you use in the discretization. But to derive the method, we can do it in a pure algebraic setting, so I'm using this linear algebra notation. So, if you look at this one, it's the matrix that you're getting looks like that. It's a sum of rank 1 matrices, dE times dE transpose, and there's some weight in front of it. And D is like discrete gradient, okay? It's 1 minus 1 at certain positions. What should we do? Okay. All right, so this is a singular matrix, of course. If we like to solve a system of equations like that, we have to impose this constraint, okay? And that is the only null vector if the graph is connected. If you have two disconnected pieces, you can have 1 here, 0 here, and 1 here, and 0 there. So, but we're interested in a connected graph. All right, to come up with a coarse version that has certain approximation property, we like to build coarse subspaces that approximate the fine spaces in certain norm. And now I'll choose some norms and procedures that I can prove this approximation property. There's a second controversial thing. I'll rewrite this as a mixed system. All right? So I introduce edge degrees of freedom, which is because L is kind of factored. So I have this portion only used to define the edge degrees of freedom, and I can put the coefficient there. The coefficient is positive. And if you solve this for this edge degree of freedom, you get this equation for all edges, and then what remains is the second portion. So it's matrix, saddle point. In this application, M is diagonal. And all these D vectors put together. And they have only 2 non-zero entries per column. D transpose is like discrete gradient, and it is also sparse. All right, so you have now two sets of degrees of freedom, vertex-based and edge-based. Okay, and in order to come up with a coarse version of that, we have to coarsen these two spaces, the edge quantities and the vertex quantities. And we like to do it in some adaptive way. So you put more degrees of freedom where it's necessary and less degrees of freedom where we don't need them to create the coarse version of this. All right, so we're building coarse vector subspace of vertex degrees of freedom and edge degrees of freedom. This is the fine space of edge degrees of freedom. This is the fine space of vertex degrees of freedom. So it's a vectors in Rn and the vectors of Rm, where m is the number of edges. And they are connected by this D operator or D matrix here. So in order to build a coarse version, we like this to be compatible. So D applied to this subspace should be mapped onto this coarse space. So there's some requirements that we have to satisfy. And also we like to be able to project anything from the fine space to the coarse space, and the same here. This one is easy, it's L2 projection. This is a little more complicated, so that this diagram is commutative. That will imply that the core system that will end up, which is also saddle point system, will be stable. Stability. All right. So now we'll try to review how we do this coarsening procedure. We'll have this graph with vertices. We'll partition it into aggregates, non-overlapping partition of degrees of freedom of vertices. So we call them aggregates. And we have a bunch of those. So how will we do this? In practice, we use some graph partitioner. Okay, and we tell the graph partitioner that we need that many subsets. Okay, that can be done even in parallel. In some difficult graphs, this is not a trivial thing, but it's doable to a certain extent. All right, so we'll have to define several subsets. So neighborhood, any vertex that is connected to the vertices in an aggregate. These are the edges where all the vertices are in the same aggregate. And this is the set of edges that the same thing but applied to the neighborhood. And we can naturally define a boundary of this one. I'll illustrate this with a picture. So this is a very schematic version of a graph, vertices and connectivity. So this, if this is an aggregate, this will be the neighborhood. So we add some additional vertices. This will be all the edges so that both of the vertices are in the aggregate. They will also have edges connected to the neighborhood, so there's, or at least one of the vertices belongs to the aggregate. And the things that are not, the edges that are not in the interior of the aggregate are called boundary edges. So in essence, I'm trying to generate a topology of these aggregates. I'll define a boundary, and when we intersect this boundary, I'll define interfaces between two aggregates. And this can be done in a very abstract way without any geometry. All right, so how do you do? So why do you need all these sets? If you remember, that's too bad. This is sum of local quantities. I can restrict this sum to subsets, and I can get local versions of the graph Laplacian. And these local versions of the graph Laplacian I'll use to compute certain eigenvectors. Okay? The eigenvectors that are in the lower portion of the spectrum I'll keep as coarse degrees of freedom for the vertex degrees of freedom. In particular, the constant will be there because it's in the null space of the local graph Laplacian. But I may need more if we need higher resolution in these aggregates. This is for the vertex degrees of freedom, how we coarsen them. So we have an aggregate. For each aggregate, we assign several vectors, one at the minimum. Okay, so at every aggregate will have a bunch of coarse degrees of freedom for that came from the vertex degrees of freedom. Okay, this is what I'm trying to explain here. Okay, so the local one that I'm using is the extended one, which covers the aggregate and the neighborhood, all the edges. So this is, you solve this local eigenvalue problem, and this is the original. You can also compute it using the saddle point matrix. All right. As I said, we select few of those eigenvectors. And since I did it on an extension of the aggregates, I restrict them to the aggregate so they may become linearly dependent. Okay, so we have to do some, for example, SVD or QR or something to remove the linear dependence. So this, in each aggregate now we have a bunch of vectors which form a matrix with orthogonal columns. And for each aggregate, I put these pieces, and that gives you a block diagonal interpolation matrix. In terms of finite elements, it's a piecewise discontinuous space. Okay? But that's okay because we are using mixed formulation. For the vertex degrees of freedom, you can use discontinuous space. The communication will be ensured by the edge degrees of freedom. As I already said, this is in the range of that. All right. The difficult part is what we do with the edge degrees of freedom. That's why I needed this boundary and interfaces between two aggregates. So if you have two aggregates, a blue and a green one, there are some edges that connect these two sets. So any such pair of aggregates defines an interface, which I call F or face, or you can, I don't know, for lack of a better name, I used the word face. And that is a set of edges, and the boundary of every aggregate is union of such faces. They are non-overlapping sets. So with each face, I'll associate several degrees, coarse degrees of freedom with the edge degrees of freedom. So I'll coarsen first on the faces. And then once I have something on the faces, I'll extend them for the edges in the interior by solving some local problems. Okay? And on top of that, there will be some, in terms of finite element terminology, some bubbles associated with the edges that are only interior to the aggregate and vanishing on the boundary. So in this way, I'll match that D of the coarse edge degrees of freedom coincides with the coarse degrees of freedom, vertex coarse degrees of freedom. So I'll ensure that the compatibility between edge coarse degrees of freedom and vertex coarse degrees of freedom. All right, that's very briefly the summary of the method. So everything involves something coarsening on the faces by selecting some vectors there, and then extending them in the interior, which involves some local solves of local problems, the local saddle point problem, and also creating this bubble edge degrees of freedom, which we again solve a local problem, but with zero boundary condition. Okay, this is the details. So you computed some eigenvectors in all this extended aggregate. So we basically, if you look at the corresponding saddle point problem, you can solve because this is a small matrix, it's actually diagonal in the first level. So we can compute these functions. So we have on the interfaces, we have a bunch of functions coming for two neighboring aggregates. And we accumulate them, or vectors. And then we do SVD to extract linearly independent subset. And those are the traces of the coarse edge degrees of freedom. All right. There's some technical detail. I need an additional function for which is arbitrary, for example, this one. So in addition to this that came from eigenvectors, I use one vector that has this property. It doesn't vanish. And for example, if you choose this one, that is satisfied. Anyway, so on each face, we have something that came from the eigenvectors and this additional vector. And we do SVD on that. All right. The extension, it's a little bit complicated in the sense that since this is we have to ensure that the right-hand side is orthogonal to the constants, otherwise this problem is not solvable. So we are given something on the faces, and we like to extend these values in the interior of the aggregates. So you solve this problem, and by choosing appropriate constant, you can make this orthogonal to the constant vector, so this problem will be solvable. So the extension is doable. All right. And finally, you have to do the bubbles. So on each aggregate, in addition to the constant, you may have some other eigenvectors, which are orthogonal to the constant. So if this is orthogonal to the constant, this problem is solvable, because the right-hand side is compatible, it's orthogonal to the constant. So we can impose zero boundary conditions on the neighborhood. So we can compute this bubble because it vanishes on the boundary. So that will be the additional degrees of freedom for the edge degrees of freedom. So basically, to form the interpolation matrix from coarse to fine for the edge degrees of freedom, we have this thing on the faces, which we constructed by doing something on the interfaces and extending them in the neighboring aggregates. And also we have these bubble things. So it's a sparse matrix, okay? But it has two types of entities. And by construction, we ensure that if you map this matrix under D, the one that was in the definition of the global problem, we actually we are into that space. Actually, they are equal. So the coarse problem that I hope I'm defining here, which is P transpose A times P. This is how we always do the coarse problem, at least in multigrid, variationally. So you get, again, a saddle point problem, and this one is stable because we have this. Oh, I didn't say that. There are some details. We can actually map the fine edge space to the coarse space, and the fine vertex space to the coarse space. This one is simply L2 projection of aggregate by aggregate. Okay? This one is a little more involved. We project onto the faces first, and then you can extend them in the interior using the basis functions and compensate with some bubbles. We project onto the bubbles. So still it's locally computable. So you do some computations on the faces and you do some computations in the interior of the aggregate. So we have these projections, and they actually commute by this construction that we employed to ensure that. It's not very long proof, but it will take me several slides. On top of that, we have a nice error bound. So what does it say? It says if you solve the problem with this in the subspace, the saddle point problem, and compare with the solution on the fine level, in this norm, I'll say what that is, it's actually comparable to the best approximation from the coarse space. This is what we typically have in the mixed method. The good thing is that this is L2, and we control that because we can control the locally, and the global L2 is the sum of the local L2 terms. For this one, we don't really have a rigorous control, but we have some indicators. So we can decide if we need more degrees of freedom on a phase or not by by solving some local eigenvalue problems. For example, you can look at the local inf-sup condition associated with the local problem. And that constant is not nice, you can include more degrees of freedom for the H quantities. And the norm is like the augmented form of the saddle point problems. So D transpose D is like divergence diff bilinear form, and this is L2 bilinear form, if you look at from finite element point of view. So you control this. So this ensures that the coarse problem, if I solve instead of the fine one, I solve this one with the restricted right-hand side onto the coarse space, I'll ensure that these two quantities are close. So we actually achieved all the things we required, theoretically at least. We have less degrees of freedom, coarse H and vertex degrees of freedom. We have approximation, and the things that we constructed are sparse. But if we put a lot of degrees of freedom in an aggregate, the matrix gets denser and denser, and you may end up with a matrix that may require more memory than the original one. So there is all these contradictory things that we have to be aware of, that one can control the sparsity of the coarse problem by using bigger aggregates, actually. That's one remedy, but that is not a rigorous argument, okay? So this is what happens in practice. If you increase the aggregates, you can control the sparsity of the coarse problem. But then you lose the approximation. Okay, so there's some balance in between. But for the examples that we did, actually we achieved all the three things: less degrees of freedom, approximation, and sparsity. So we need less memory than the original problem. There is another thing. You end up with this problem, and the question is how you solve it. Do we have a good solver for this one? If the problem is relatively small, which people assume in many applications when do two-level upscaling, they do direct solve. If you can do it by direct solve, you don't have to worry about that. But in general, this may be as large. I mean, capital H can be several times bigger than the fine mesh. So still that may be large enough, okay? So you need a good solver for that. So luckily, this procedure that I explained, you can apply it recursively. So you can apply the same argument to this matrix and create a hierarchy of things. And if you care about a solver, so on the next levels, you don't have to be very accurate. You may you may need only 1 degree of freedom per aggregate on the coarse level, just for the solving purposes, because you don't care about the approximation too much. So this is in this application, this is solvable. All right. How much time do I have? Okay. All right. Yeah, I said that, but I didn't list it. So this quantity, what is that I listed here, we can control because you choose enough eigenfunctions aggregate-wise, and because this is L2, if you ensure it locally, by summing up the local estimate, you can make it, you can control that globally. So we do have approximation for the vertex degrees of freedom. Okay, now let's do some examples. So to show that this works because it's an algebraic method, we try this on a graph, internet graph. So this is the size of the graph, not very big. We we partition it into 100 aggregates, so different colors correspond to different aggregates. So you see how irregular this can be. Some are much bigger than the others. But, and with each aggregate, we'd associate all these degrees of freedom, and there's some interfaces, etc., etc. All right. So what did we do? This is the number of degrees of freedom that we allow per aggregate. We can increase them. This is the size of the coarse vertex space that we get after we do this type of coarsening. This is the size of the coarse edge degrees of freedom. Operator complexity is the number of non-zeros of the original problem plus the number of non-zeros of the coarse problem divided by the number of non-zeros of the fine problem. So it is 1 plus something. If that something is less than 1, we are good. So we require 37% memory of the original problem, for example, in this case. So the error. The error is for the vertex degrees of freedom is in L2. So the relative error is, you see the percentage that you get in with 6% with that many degrees of freedom. And for the edge degrees of freedom, this is the percentage that we get of the error. Okay, so I think it's very good with that number of degrees of freedom and with this memory requirement. All right, there is a legitimate question because we can do the coarsening without going to the mixed formulation. Because the vertex degrees of freedom depended only on the local graph Laplacian, which we can do independently of the edge degrees of freedom. And for people that know multigrid for finite volume, they know that piecewise constant don't really work. Okay? So if we do coarsening directly to the graph Laplacian with the same P that we constructed for the mixed method, you get much worse error. So actually introducing the edge degrees of freedom helps us, although we increase the size of the problem to begin with. All right. So, and one explanation is exactly that the piecewise constant for two-grid method for finite volume doesn't work. We have to do something in addition. All right. To demonstrate the approximation property, we did the following. This graph Laplacian, you can solve the minimal eigenvalue problem, the minimal positive eigenvalue problem. And you get an eigenvector. That eigenvector is orthogonal to the constant. It has negative and positive entries. If you divide the domain into two subdomains corresponding to the positive entries and to the negative entries, it kind of gives you spectral partitioning with balanced components. So you computed this vector is called Fiedler's vector. So you computed this partitioning, and you use similar thing on the coarse graph Laplacian, and you see that we get something similar. It's not exactly, but it kind of captures the features of the original partitioning. If you put more degrees of freedom, you get better resolution, of course. It's much closer to that one. And this is a nonlinear problem, okay, for which we actually don't have a theory, but for the linear one, we do. All right. This is in the same thing in a table form. So we also computed the edge cut. The edge cut is the number of edges between these two subdomains. So the Fiedler vector kind of minimizes the edge cut, the edges that connect these two subdomains. So it actually also, this is the best, and what we get with this, it does not really capture that close, but it's maybe for practical purposes it's okay. The error is not that great. This is nonlinear problem. The minimal eigenvalue, though, you're getting there, okay? Minimal positive eigenvalue. Okay, what else? Oh, the first one was a linear problem. This one is actually solving eigenvalue problem using the coarse graph Laplacian. In the previous one, we put the eigenvalue problem, the eigenvector is the right-hand side with the lambda, and you restrict that to the coarse problem and try to see if we can actually have a chance to approximate it. And this one is the nonlinear. All right, that's the picture with the nonlinear. All right, now let's do the finite volume. Here, this is not. It's a local problem. I mean, it's a local graph Laplacian. There's because we have geometry, the connectivity is controlled by the geometry, so everything is nice. It's not like the graph Laplacian, the other one. So using two-point flux approximation, we end up with something like that, with the differences between two volumes, and there is some transmissibility coefficient. That is the one that we have in the weights in the graph Laplacian. So it's exactly graph Laplacian with positive weights. All right, so we applied this to some benchmark problems. This is, many people use this as a test. These are the characteristics, volume size. We did portion of it and the whole thing. And the challenge here is the variation in the coefficient. It's also anisotropic in one of the directions. Okay, the first example, this is the degrees of freedom per aggregate. These are the original size, and this is the reduced dimension. These are the operator complexity. So this one requires 54% memory than the original one. And these are the errors for the pressure in this case, and this is for the so-called velocity in the finite volume discretization. All right, it's not that great, but it's good, I would say. The full model is that size. These are the coarse version. Vertex, and these are edges. Operator complexity the same. It's pretty much the same as before. So the full model is also, we can come up with the upscale version with that quality if you're happy with this percentage of the error. If you want to get more, you have to put more degrees of freedom, and this will increase. It increases in some way, okay? All right, there's another, this is much simpler problem. So the variation of the coefficient is not that great. So it's 100 times minimal and largest value. And it's kind of unstructured mesh. And you do the partitioning. And the coarsening, and we have much better resolution here because the problem is not that difficult. Okay, which is to expect. We like this method very much because it's algebraic, and we're working on a parallel code. So there's some initial result that Chuck is working on. So there are many aspects of the code. One is to generate the partitioning, and then to do the building the interpolation matrices. And it's timings for various part of the algorithm. So if you increase the number of processors, this is the time. So the thing that we care about is timing. Okay. So it shows good scalability, and even we tried this one, and there's some also good results in that direction. So to conclude, if somebody gives a matrix in this saddle point form, everything else is totally algebraic. We don't need anything else. It's a kind of black box thing. The things that we care about is how many eigenvalues you can put, or eigenvectors. And other than that, the method is totally automatic. If in this application, of course, there is geometry, so you should use it. I mean, I'm not married to the algebraic methods per se. I mean, you can use geometry because it helps a lot. You can come up with much better partitioning and things like that. And also, one may say, okay, you did this very sophisticated method for this simple problem. I mean, sum of low-rank matrices. What can you do for other problems? Actually, we're working on that. And for any finite element problem which you can assemble from local element matrices, you can come up with the equivalent mixed formulation by introducing some, because the matrices, you can factor the pieces in between. And that is work in progress, and it actually, the theory is done. We can do, for example, elasticity like this. Okay? But not H-curl, I don't think we can do H-curl like that. But that's still something. Okay. So, thank you.